Okay, in this video we're going to talk about solubility. So previously we talked about how solutions are made. Solubility is a characteristic of the solutions. It is the maximum amount of solute that dissolves in a fixed quantity of solvent at a given temperature. So really solubility is a concentration. It's usually measured in concentration units of either moles per liter or molarity, or can be measured in terms of mass per volume, like grams per 100 mils or grams per liter. Since it is measuring a concentration, we look at concentration units for solubility. Solubility is also an equilibrium process. So our idea of dynamic equilibrium also applies to a solute dissolving in a solvent. We have two competing processes going on. We have dissolving of solute molecules into the solvent, and we have recrystallization of the solute molecules back to the solute state. Both of these processes are occurring at the same time, and when they reach the same rate, are at an equilibrium. So solubility is an equilibrium process. Do we have more of the solute dissolving, more of it recrystallizing, or are they occurring at equal rates? So we can define this based on a couple of vocabulary words. Saturated solutions mean that we've reached that maximum solubility. We have all the solute that can possibly dissolve under the given conditions, and the concentration of the solution is then equal to the solubility. Unsaturated means that we haven't reached that maximum concentration yet, and we can still dissolve more. Alright, so our rate of dissolving is greater than our rate of recrystallization. Supersaturated means that we've passed the solubility point, we've passed that maximum concentration, and we really have more of it dissolved than we were supposed to, than the equilibrium will allow. And we'll talk about how this is possible. Supersaturated solutions, either through a given change in the temperature, as in heating up the solution to try to dissolve something. I think this is a trick we've all tried in a lab once. If something's not dissolving, increase the temperature, right? As we increase the temperature, the solubility increases. We get more of it dissolved. But then we have to cool down that solution back to whatever temperature we need to work with it at. If we cool down the solution rapidly, we could freeze some of that solute into the dissolved state and not allowing it to fall back out of solution. This would create a supersaturated solution. And these are highly unstable, and even the slightest change, like adding one more crystal of the solute or even tapping the glass, can cause the immediate recrystallization of all that excess solute. So we can see the tiny crystal spinules coming out of solution very quickly until the whole thing is filled with all those excess crystals of solute. So we know temperature has an effect on the solubility. That's why we increase the temperature of our solution when we're trying to dissolve things. Temperature shifts solubility. Usually this is increasing temperature will lead to increased solubility, but that's not always true. Alright, so if we look at our diagram here, at lower temperatures, we have less of the solute that can dissolve into the volume. As the temperature goes up, more of the solute can dissolve. But it doesn't always have to be that way. We have two types of solutions based on this temperature change. The first is the one we're most probably familiar with, endothermic solutions. Usually this happens when we have a solid that is dissolving into a liquid. Like if you're putting sugar in your tea, putting salt in the water to boil. Most solids require excess heat in order to dissolve more rapidly or to dissolve a greater amount of the solute. So these are endothermic. We can write them as the equation where the heat is on the reactant side to produce our aqueous solution. The other type of solution is exothermic. This is the opposite. where if we increase the temperature, we actually get a lower solubility. And this is mostly associated with gases. If we are trying to dissolve a gas into a liquid, so we're trying to dissolve O2 molecules into water, it's an exothermic process. Heat is actually released during the dissolving of the gas into the liquid. And if we think about our gas properties, it makes sense. Gas molecules have a large amount of kinetic energy. They don't associate with other molecules. If we're forcing them to interact with liquid molecules, they have to release some of that energy. We're forcing them to have the intermolecular forces. So that is an exothermic solution. Heat is going to be released. So if we increase the temperature, we're actually giving more kinetic energy to those gas molecules, and they're going to escape the solution. So that decreases our solubility. So if we look at solubility curves, this gives us a graphical analysis of how this works. All right, so on the y-axis we have the solubility, the concentration or the mass per unit volume, and on the x-axis we have the temperature. So for dissolving a solid like KNO3 into a liquid solvent, we see an increase in the solubility as the temperature increases. And this green line represents the saturation line. It represents the solubility, represents the maximum concentration we can have at that temperature. So if we're below this green line, we're in the unsaturated area. We could fit more solute than we have. If we're above the green line, we're in a supersaturated area. More of it is dissolved than should be able to be dissolved. So by using this graph, we can actually look at numbers and determine the concentration at given temperatures and how many grams we could have. So our first question, how many grams of KNO3 are dissolved in 100 grams of water at 30 degrees Celsius? So if we notice our units, the solubility is grams per 100 grams of water. So let's look at our temperature. At 30 degrees, go up to the green line, we can only have about 49 grams of KNO3 per 100 grams of water. Alright, so if I wanted to go to the second question, if I wanted to have at least 115 grams dissolved per 100 grams of water, what is the minimum temperature I can have? Alright, so now we're going to start on the y-axis. So 115 grams is about here. We're going to go all the way across to our green line, and it looks like we need to have a little bit over 60 degrees Celsius. So maybe 62 degrees Celsius in order to get all that 115 grams dissolved. So let's look at what happens when we have too much. If you dissolve 90 grams at 50 degrees, all right, so here's 50 degrees and 90 grams, so we're sitting right on the saturation point. Then we decrease the temperature to 10 degrees. All right, so if we decrease our temperature starting at 50, and now we're going to decrease down to 10, but we still had that 90 originally in here. All right, that's way too much than we can have at 10 degrees. How many grams of KNO3 will fall out? Well, we started with 90, but at 10 degrees we can only have about 23 grams. So 90 minus the 23 that we can keep gives us the difference that we need. So 67 grams approximately is going to fall out of solution from that temperature change. There are different solubility curves depending upon the solid. So this graph shows you several. So our green line is still KNO3, but there are several other on here. So you'll see that most of them increase with temperature, those endothermic solutions we talked about, but it's not always the case. So this one down here is an exception. This is exothermic, and then the solubility stays the same regardless of temperature after that. So it's never 100%. So we have to look at the curves in order to figure out what's going to happen. You'll notice that some of these curves are dramatic in their increase, like our KNO3, but others decrease or increase very, very slowly. So sodium chloride doesn't really increase solubility that greatly over a large temperature range. So we have to look at the curve. Solubility curves of gases go the opposite way. So the exothermic solutions, we see that as the temperature increases, the solubility decreases because those gas molecules are escaping with that increase in kinetic energy. They're getting away from the water, they're being released back out into the atmosphere. It's the same reason that we try to keep our Cokes cold, right? We're trying to trap the carbon dioxide. If your Coke warms up, the CO2 is going to leave and it goes flat much faster. So keeping the temperature cold increases the solubility for exothermic solutions. Alright, besides temperature, pressure also plays a role, but only with trying to put gases into solvents. So pressure, of course, affects how close together gas molecules are. If we increase the pressure, we increase the connectivity between the gas molecules, we push them closer together. And if we're trying to push them into a solution, we force interactions with the solvent molecules. So increasing the pressure increases solubility of a gas going into a liquid. It does not change the solubility of two liquids or a solid going into a liquid. Henry's law is a way that we can use to determine the effect that solubility and pressure have with one another. And it's a very simple equation. It says that solubility of a gas, the concentration, is equal to, and this is Henry's law constant, it's a proportionality constant. It's a constant value depending upon what gas and liquid you're trying to make a solution of, times the pressure or partial pressure of the gas. Right? So how much pressure is being put on the gas to go into the solution. So as we can see, as pressure increases, solubility increases because K is constant. So let's think about what's going on in our example problems. Calculate the solubility of carbon dioxide in water at 0 degrees Celsius and 3 atmospheres of partial pressure. Solubility of carbon dioxide is 0.348 grams per 100 mils of water at 0 degrees Celsius and a partial pressure of 1 atmosphere. So this second sentence gives us our KH value, or Henry's law constant. Alright, because our pressure is 1, so 1 times this value tells us our solubility. So this is our KH. Even if we didn't realize that's our KH though, we can look at the difference in the pressures. So we have the solubility at 1 atmosphere. What is the solubility at 3 atmospheres? Since it's proportional, we're tripling the pressure. Therefore, we're going to triple the solubility. Alright, so tripling our solubility gives us the new solubility at the higher pressure. Alright, our second question down here has to do with a concept idea as well. So let's think about what's happening. Elevation of Lake Havasu is 400 feet. Elevation of Lake Tahoe is 6,200 feet. Okay, so what do we know about the pressures at different altitudes? Okay, we know that the higher the altitude, the lower the pressure is going to be. If the water temperatures are the same at the two lakes, which lake has a lower concentration of oxygen gas? Alright, so if Lake Tahoe is much higher in altitude, it's going to have lower pressure compared to Lake Havasu, which is going to have a higher pressure, being closer to sea level. We can determine what we know about the concentration of oxygen gas based on those pressures. Alright, since Lake Tahoe has a lower pressure, it's going to have a lower concentration of oxygen gas as well. Lake Havasu, having a higher pressure, is going to have more concentration of oxygen gas. Alright, so that concludes what we're going to talk about with the different properties dealing with solutions. Thank you.